Hello, everyone. I'd like to discuss a LNA design, and here are the requirements for this amplifier. The operating bandwidth is between 5.725 and 5.875 gigahertz. The S parameters, they are to have a magnitude of S11 under 10 dB, also S22 under 10 dB, and the magnitude of S21 should be greater than 15 dB, a noise figure less than 2 dB, and unconditionally stable. This design was done in QUCS, it's QUCS, it's an open source design program, and we utilized this RO4350B substrate with a relative permittivity of 3.48. And to start off, I set the DC bias by looking at this graph. For maximum linearity, it's good to pick one of the graphs in the middle. So I went with number 6, which is 50 microamps base current and a VCE of 2 volts, and that puts you at an IC of 15 milliamps. And if you take those numbers and go, you can find the S parameters, and they're all laid out here. And notice that S12 is 0.06, which is very small. So we utilized that to make the approximation that it's unilateral, which helped later on in the matching section. So now, when you have those bias values, those levels, you can then set the values for the bias network. And without going into all the details, you can find the values for these resistors. There's R1, R2, and R3, and that will put it at the correct biasing. And the important thing here is R3 is 200 ohms, and with 15 milliamps of collector current, that drops it from 5 volts down to 2 volts, and that gives you the 2 volt collector to emitter range. And then on the base side, we set the voltage correctly with these resistors here. There are also inductors to block the RF and getting into the DC, and also these capacitors which block the DC. So, moving on, we have the stability, which needs to be unconditional. And so you calculate this delta from this formula here and take the magnitude of it. And if it's less than 1, and this K value, which is the formula is here for that, if that's greater than 1, then you can be sure that it's unconditionally stable. Then we have the gain design, and again, we made the assumption that it's unilateral, and then we were able to use this formula here, that gamma out is the conjugate of S22. And so we start with that, and we go into the Smith chart here, And now we're working on the output matching. So we start here on the Smith chart, and then the collector, resistor, and inductor moves it to this value here. And then we have the line, the transmission line here, which swings it all the way up to the top. And then this open stub brings it to 50 ohms. And you can see here that this first column that I'm showing here represents the inductor and resistor attached to the collector. And that's going to affect the impedance. And then this is the transmission line and this open stub, which gives us the matching 250 ohms. So this is used instead of the lumped elements. Secondly, we move on to the input. And we can say that gamma source is the conjugate of S11. And that similarly gets us to 50 ohms in the center. We start here, and the transmission line brings us up to this circle, and then this open stub gets us back to the center. And the numbers are here of how long those two are. After all of that, we ran the simulation, and we found out indeed we had S11 under negative 10 dB. S22 is also under 10 dB. And then S21 is in fact over 15 dB. And then also we had the noise figure requirement that it had to be under 2. Well, Fmin is 1.23, and with these other parameters and the fact that we chose gamma S to be S11 star, we could find that F is 1.31, which is well under 2. So that concludes this quick video on the LNA design.